for the sake of the recording, we're looking at, what is it, week 6 is what it was? Yeah. The week 6 worksheet. I think it's the first question. All we're trying to do is be able to find the relationship between the structures in the box. The easiest way to approach this is to first acknowledge that they aren't in the same viewpoint. And so to come to any kind of interpretation between those molecules, you have to get them into the same viewpoint. Okay? My personal preference would be to move to the overhead view. The overhead view is easier to interpret and visualize, and therefore what I would try and do is get them both into the overhead view. On an exam, straight up, a couple things. One, I don't think I would ask this on an exam. Okay? It's requiring you to do a whole bunch of stuff to be able to manipulate and see these things. Okay? Homework, fully fair game. But on an exam, if I was tasked with this question, first and foremost, I would skip it. Okay? It involves way too much thought process for me to deal with, and I would come back to it at the end. The next part, converting them both into the overhead view would allow me to get into a system that would allow me to compare them, but that's a lot of time to convert both into an overhead view. So on an exam, what I would try and do is pick whichever of those drawings I like better. Do I feel I understand and can draw chairs? Then I'm going to convert the Hayworth, we'll call it the red one or the right one, into a chair. If I feel I can interpret Hayworth better, then I'm going to convert the chair into a Hayworth projection. Does that make sense? So that way I'm only making one interpretive leap and then making the comparison to answer the questions underneath. Okay? For our sake of visibility and moving through it, I think you should take it to the overhead, and you need more practice with recognizing what the overhead view means. The chairs in the Hayworth don't show up as much through the rest of the semester, so it's more relevant to look at those overhead views because those are more standard kind of default drawings. Okay? So how do we start this? Find a focal point. For me, the focal point is that oxygen within the ring. Okay, so I would draw out my rings. When I draw that out, what I'm seeing is that oxygen is on the right-hand side in both of those drawings. So I'm drawing it towards the right-hand side. Okay? In the Hayworth projection, if we looked at this, remember the Hayworth is taking the ring, let's call it the iPad, okay, our ring, and turning it on its side. If I were to fully do this conversion, I would argue that we should be converting that Hayworth into this orientation of the ring. Whoops, not the oxygen there. The oxygen up there. Everybody see that? Okay. Why did I not do that? Because if we look at the skeleton I've drawn out for the red, the first one I drew didn't show it as the bottom one. It shows that as the top one. I've done a rotation. Why would I start immediately with that rotation? Does that make sense? Do you understand the question I'm asking?
Yeah.
Okay, because it is a little bit of a weird question.
Because the chair flip doesn't show it in the same location?
Chair flip, yes.
Because the point
I think
is
I
there.
agree.
It's not like
Yes.
the oxygen is in the center of the whole
Right.
thing.
How did I start my analysis? I started my analysis with the chair, which meant I drew this structure. The Hayworth isn't aligned in the same thing. The subsequent questions are asking me to make comparisons between the structures, which means I want those structures as close to the same orientation as possible so that I can make a fair comparison. The Hayworth initially would be easier to draw from the overhead, as this bottom one is kind of showing, but that means I would have to do another interpretation to get it up to that. So what I'm choosing to do is that secondary interpretation in my head, dangerous, but that's my choice. Instead of drawing it directly straightforward out of what the Hayworth looks like, I'm choosing to draw it in an orientation that would align better with how I'm starting to draw the overhead for the chair. Does that make sense?
Okay.
You get it?
I don't know why I was thinking those were the same.
Yeah, it's a very, very slight rotational change. Okay? And for me, that slight rotational change is small enough that I'm not going to be too stressed about it. If you're looking at it and being like, that's too much, that's okay. draw out that other version of it and then kind of shift across. Right? I've picked my focal point being that oxygen, so we'll go with the blue. And now it's a question of filling out the rest of those groups. I can either move what I would argue is counterclockwise around the ring. That's a bad idea to write that. Or I could move clockwise around the ring to place the atoms. Okay? As long as I'm consistent in my approach, it ultimately doesn't matter. Okay? I'm going to go clockwise. So from the oxygen, I'm going to go to the right, which means I'm going to go to here. So now I know at that spot I have an OH. Okay? As I continue to move around, I see I have another OH. Everybody picking up on that? Another OH. Another OH. And then we might, since we went in this pattern, be like, oh, there's another OH. We got to be a little bit careful with that. To get to that OH, what did I pass through? A point, and that point is a carbon. We could just leave the point there and not worry about it. Okay? I already talked about, because a lot of people started to draw this, which is good. That's a good first step. Okay? But there's some issues behind this. When we look at the chair, okay, there's my eyeball up here. Okay? So the chair is looking at, the iPad is now the ring, right? iPad looking at it from the side, okay, is the chair. That carbon, my CH2OH, the red arrow, is up here. Right? That's what that shape means. Where that line is drawn is saying it's up here. Does that make sense? Okay. What does that mean? Well, stay there. Fine. Go over here. Okay, it's over here. If I'm looking at it from the top, where's that bond aimed? At me. Does my drawing show that? No. Where's my eyeball with respect to this? It's here. It's out in front of the page looking down on the molecule, which means this bond isn't accurately reflecting that molecule. I need to make sure it accurately reflects it by changing it from just a solid line to a wedge. Okay? That can be a really difficult bond to pick out. That is officially an equatorial bond. So what we could go through and do is draw the axial bond at that position, straight up and down from the point. That one is very clearly aimed away from my eye, which means that one must be aimed at my eye. Kind of, sort of? We should apply that logic the rest of the way through. Is that a hand?
Yeah, so you only draw the one wedge on the carbon, nothing for the OH.
I don't have to specify anything for that OH because this wedge is really only specifying that carbon of the ring. We're saying where that bond is with respect to the ring. Is the oxygen connected to that carbon? No, so I don't care. Okay? If that was also a chiral atom, then would I need another bond? Yeah, you're right, I would, but it's not a chiral atom because it has two hydrogens.
Okay.
Make sense?
Yeah.
Right? So we should continue that logic through the rest of them. Do you think you understand how you would do the wedges and dashes for the rest of them? Can I just draw the answer, or do you want me to walk through them? Okay. You'll have a second opportunity to complain in a second. That one should be dashed. This one should be wedged. This one should be dashed. This one should be wedged. Do you want me to walk through any of those assignments? Or are you okay with those being all wedges and dashes as shown?
Can you walk through?
Yes. We'll go the clockwise direction, so to that first oxygen. Okay. Identifying whether it should be wedged or dashed can be challenging because it's located in the equatorial position. This is where I would draw the axial. My eye is above the molecule. Is this axial above, coming at my eye, or away from my eye? Away. If it's going away, that red line would be dashed, which means the oxygen must be wedged. There's the wedge. Okay. If we move to the next spot around the ring, same deal. It's equatorial. The equatorials are always challenging, so draw in the axial. The axial always points up, down from the point of our ring. The point of our ring being shown in green. Okay, that point is aimed upwards, so my axial is aimed upwards from that point. It's aimed upwards, which gives it away. If it's aimed upwards, that should be wedged, but I'm trying to draw the oxygen, so the oxygen needs to be dashed. That was a deep sigh. Is that a deep sigh you're getting it, or a deep sigh otherwise?
It's kind of confusing.
Absolutely
So
is.
if it points up, it would be wedged?
If the not nice answer, not always. If it points up, it should be wedged in this case. Yes. Why in this case? Absolutely. If it points up, it should be wedged. It's all in reference to where your eyeball is. So if I change the eyeball to being down here, pointing up is now away. Does that make sense?
Yes.
Okay. So cool. So we're good?
Yes.
Okay, that's fine. I want to make sure. Okay. Then we go through and look at the red one. Same process with the red one. We'll go clockwise again around this. So we're going clockwise around. Okay. This one should be a little bit easier, and hopefully we can see almost right away that that oxygen should be dashed. Yeah? Next oxygen should be, next oxygen should be, it's kind of hard to see. 1, 2, 3.
Is it the one that, oh, never mind, wrong one.
It's one of the reasons why I don't like Hayworth projections is those bonds start to overlap, particularly when you're looking at carbohydrates. Okay. The next one. And then the next one. Dashed. And that's again going to a carbon that then goes to our oxygen. Just because I saw someone do it, let's double back. Pseudo-anonymously referencing it. Is that a methyl group? No, I understand where you're going. There's a carbon there, so you've acknowledged the fact that there's a carbon, but that carbon also has an oxygen connected to it. We should be having that oxygen connected through. Could I write Me then OH? No, because the Me means very specifically CH3. Okay, and that's a CH2. Whoops. Make sense? Okay. Now we've got them in the same viewpoint. So now we could theoretically move through that massive flow chart, which what I tried to do within the boxes was highlight the questions or the important questions, branch points within that. So we could try and look at our molecular formulas, okay, and counting it all out. You should do that through practice, but what you should find is the formula is going to be C7. Did anybody actually count it all? I get 11.
I got 11.
You got 11? Okay, we'll say that's right then. Oxygen, 1, 2, 3, 4, 6. Should be getting C7. H11 makes me a little nervous.
Why isn't it 12?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 12. Oop, and it's not C7.
It's 6, right?
It's C6. C6, H12. What did we say? O6? Yeah. Why did I say 7? Here's the mistake that I did. It's a 6-membered ring, so I said 6 carbons plus an extra one hanging off. There was an oxygen in that ring. There's actually only 5 carbons in the ring. The H11, I think the one, there's 2 common ones to miscount. It's going to be where the CH2 is connected, that carbon, and then I think also this carbon is the other one I was missing, okay, when I miscounted. And I counted it officially twice in my head, and both times came to 11, and so both times made a consistent wrong mistake. Okay, so we have to be careful as we count that out. You should get the same formula for both. Atom connectivity, that says atom with an O for the record. Okay, do they have the same atom connectivity?
Yes.
Yes, everything is aligned, connected to the same spots. Okay, the orientation where those atoms are located has changed. Okay, but the atoms are still connected to the same spaces or the same spots. Okay, are they mirror images?
No.
Okay, this is not going to be an easy one to explicitly see right out of the gate, unless you're just good like that, in which case you should probably keep your mouth shut because the rest of us are pissed. What I would argue I would do is I would take the one on the right, and I would take it, yeah, I mean, you can flip it over that way. I was going to flip it this way. Okay, you pick a direction that you can consistently flip it, okay, and redraw that structure. So for me, I'm taking it and flipping it to the right. It's going to get the same answer as if you flipped it to the left. It's how you see it when you go through that process. So if I flip that over, the oxygen, now I got to really look at it. I don't know why I got to turn and look at it on the screen, but whatever. Okay. I'll get my oxygens all connected around. All of that should be straightforward. Okay. As I flip it, it's ultimately not really going to matter with that one. But now it's figuring out all the wedges and dashes. Okay. That carbon, it was back, right? And I flipped. Now it's coming at me. That needs to be drawn as a wedge. Okay. This oxygen was coming at me. Now going away. Dashed. Okay. And hopefully what we notice as a pattern is that as we do the flip, they all exchange their locations.
So they basically become opposite of what they were.
They become opposite of what they were. Because what you've done is you've changed your eyeball, effectively. You're now looking at it from the underneath. Okay? So now it would be trying to align that up there. I'm really nervous about trying this, but I'm going to try it anyway. I'm just going to do that, see if that works. That was a really bad idea. What I want to do is bring this up so that I can see it. Maybe I can bring it down. No, I don't think that's going to work. So that I can see the mirror image kind of sitting in between. You guys see what I'm trying to talk about? So I want to see this in comparison to this. And if I look, it does mirror, right? If I had my mirror plane right here, the oxygen would immediately reflect across to the oxygen. Carbon would reflect across, carbon would reflect across. Does it kind of make sense? This oxygen was wedged. As I reflect through that mirror, it should stay wedged. It should just be on the left-hand side of the molecule. So if we're looking, okay, mirror's fine, mirror's fine. That's not mirroring. Okay, so we could say this carbon is mirrored, but this carbon is not mirrored. Okay, as soon as you encounter one that is not mirrored, what does that mean about our mirror images? They're not mirror images of each other. Okay, because they're not mirror images of each other, we could, the superimposable is an earlier question. We could check the superimposability. If we took this and tried to overlay it, would it superimpose? The background ring would, which is why I picked this orientation to align that for that superimposability. I just did it unintentionally. Okay? But then we could see where all the connectivities were. Okay? And we would see it doesn't directly superimpose either. So that's also a no. Okay? For the sake of what I kind of wanted you to do within this question, okay, this is our mirror image structure. This should be drawn next to the blue one so that you could see it. Does that make sense? The blue one here should be drawn next to this red one so that you can see the superimposability. So for answering the superimposability in the mirror images, that should be a lot of drawing so that you can put those structures next to each other so you can clearly see it for yourself. Mirror images can show up anywhere. Okay? So wherever you decide to see the mirror, that's fine. draw it for you. That's what I'm intending you to try and go through and do. Make sense? The final thing, or final kind of overall question, is now what's the relationship between them? As we've gone through and done these, you're just kind of moving through the flow chart, okay? Because they have the same atom connectivity, because they're non-superimposable, and because they are not mirror images, the relationship is diastereomers. Okay? So it's really the catch-all leftover bucket. Does that make sense? And Nate, you asked.
Yeah,
Does that cover everything? Okay. I like this question for homework. I don't like it for an exam. Okay. So this really, I think, pushes back, covers all of the stuff except for like hybridization, but a lot of what we were trying to do in Unit 1, getting comfortable with those three-dimensional shapes and their relationships. So I think it pushes a lot of that, and it gives us the different relationships, so I really like it for that reason. But yes, it's way too much for an actual exam question.
On atom connectivity, if one, like an example, if any of the OHs was just an O, would that mean no atom connectivity?
Which, you're actually asking a question that I was wondering about through this process. If we deleted one of those H's, I'm going to delete it from the top red structure. Can I erase the bottom red structure? Okay. How would we answer atom connectivity? I would argue it's a moot question. It makes no sense to actually look at atom connectivity. It makes no sense to look at superimposability or mirror images. Why?
Because they don't have the same formula.
The molecular formula is different.
Oh, okay.
So as soon as the molecular formula is different, they're different. Like, why make a comparison? Okay? We don't compare oranges to, I was going to say grapefruits, we would make that comparison. Oranges to cats. There's a good one. Okay? Those are different phyla.
File?
I don't know.
No, they're different kingdoms.
There we go. That works. They're different kingdoms. It doesn't make sense to do a good comparison there. We're not going to find a whole lot of useful things in that comparison. Okay? Because it's too different. So if we deleted that hydrogen, that wouldn't make sense to reference atom connectivity. Where we could see atom connectivity would be if I took that oxygen and I connected it here. Now I do have the same molecular formula, right? But I've now changed the location of the OH. The atom connectivity is now different. Okay? Because the atom's connectivity is different, do I care about mirror images? No. Do I care about superimposable? No. Okay? So I did try to structure those kind of questions somewhat according to the flow chart, though I believe these two are inverted. I think superimposable should happen before you look at mirror images.
Are we gonna have any of this on this test? Yeah. Okay.
Week 6, yeah. I do want to keep it a little on the lower end, so I will ask for the relationships between structures, but what we'll probably keep them to, and I can't promise it, but probably keep them to. Calling it overhead is a bit of a kind of cop-out. I'd say the line angles. So where we're looking at things more along these lines, maybe throwing a ring in there. Okay. But I don't think I would draw anything with so many wedges and dashes on it, because that's just a lot going on. And I don't think it's worth reiterating the pain of those, of our chairs and our Hayworths.
In the hybridization part, just below, it's like I labeled it letter B.
Let me hold on, because you're changing the question,
Yeah.
right? So let's make sure we don't have more questions about this first, but then I'll come back to you, okay?
It's a different question, but are you gonna tell us like how many questions per like subject that you did last time? Cause that was different.
I might have, I have to write it.
Okay.
I have to write it, but yes, I will try and do that. Because as you mentioned that, like, I think I had that done by this point last time. So I should have that done before this weekend.
Between those two molecules, those wouldn't be considered isomers at all, right? Or
Because they have the same molecular formula, they are isomers. The relationship is that they're structural isomers. Also known as constitutional isomers, if you see that out there. Make sense? Okay, hey, hybridization. What was the question?
It was the part where it was saying identify hybridization for each non-hydrogen atom.
Mm-hmm.
What does that mean? Like, am I just focusing on the ends? And I don't understand.
See the red dot?
Mhm.
Is that a hydrogen? No.
It's carbon.
So, what's its hybridization?
sp3.
How you did that made me a little bit nervous. You could very well have done it right, but it makes me a little nervous. Do you see the blue dot? Is that a hydrogen atom? No. What's its hybridization?
sp2.
Okay, so you just did it very well all in your head. So, yes. Okay. So what the question is saying is there's lots of atoms in here. The nitrogens and the oxygens and the sulfur, for that matter, are explicitly stated because that's a requirement. If we think back to Unit 1 with how we draw things, we have to specify non-hydrogen atoms. Or sorry, non-hydrogen and non-carbon atoms. We have to be explicit in stating those atoms so that we know they exist. Okay? So when the question is saying identify the hybridization of non-hydrogens, so every atom in here, if it's not a hydrogen, I want to know its hybridization. Because the hydrogens all have the exact same hybridization. What's the hybridization for each of the hydrogens?
Wait, no, sorry,
No.
SP,
No.
SP2.
The hydrogen's a weird one. What's the hybridization of the hydrogen?
It just has one bond.
It has
So it's
just one bond.
S.
It's just
There we
S.
go,
It's
there
the
we
only
go.
orbital it's got. It doesn't have to actually hybridize. It stays as its atomic orbital. Okay? Yes?
So for the nitrogen and the sulfur, we would not assume there are any extra hydrogens because they're not specified.
True. So the only time we can imply hydrogens is on heteroatoms, non-carbons. Sorry, the other way around. The only time we can imply, man, I have no idea what I just said. So let's rewind all of that. Okay? The only time we can imply hydrogens is on carbons. So all other atoms, you have to specify the presence of hydrogens. So when I look at this bottom nitrogen, there is no hydrogen implied. Could I imply something else? Yes, in fact I am. We're implying lone pairs. And that's why we can't imply hydrogens on it because we don't know which one we're implying. Are we implying lone pairs or are we implying hydrogens? So anything not carbon, you have to explicitly state your hydrogens because we will imply lone pairs.
And it's always implied that the octet is full.
And it is almost. It's not always implied the octet is filled.
Unless there's
If there's a charge, that could be breaking our octets. Right? So it's always assumed that there's an octet, and if you're breaking from that octet, there's a charge. And the charge is explicit.
I mean, on that carbon we can't imply lone pairs on that carbon. Because
True.
it's implied that there's hydrogen. So therefore,
Is it implied there's a hydrogen?
it's not implied because it's written there.
It's actually explicitly written.
Yeah, but like say if the H wasn't there, but it was just 1+, then you're not.
So, and that's an interesting statement because we can technically do that. It's just the drawing software I've got won't let me do it. I could do this.
Yeah.
That is absolutely technically allowed, fair game. Okay? What does that mean?
It's only connected to one hydrogen.
It's only connected to one hydrogen. There's only a single hydrogen implied. Because if there were two hydrogens implied, what would its charge be? Neutral. It's showing charged, which means it can't have that other hydrogen there. Okay? So the positive charges on carbons can be misleading, and you got to be a little bit more careful with those. The positive charges on every other atom that you'll see aren't misleading, because they will still have their octets. So it's the positive charge on carbon that gets nasty.
So does it have, another electron left?
So if we consider it, carbon has 4 valence electrons. We're told that it has a positive 1 charge. Okay? Bonds, okay, if we're looking at it that way, bonds, it has clearly 2. 4 minus 2 would be a plus 2. Okay? It needs to be a plus 1. So what if it was a lone pair? Well, then that would be 2 electrons, right? That would be 4 minus 2 minus 2, which is 0. So it can't have a lone pair. How do I get it to be plus 1? I have to subtract 1 more bond. That's the presence of that hydrogen. Okay? Where you could potentially maybe encounter, I think the question you're getting at is, what if I made it negative? Okay, what if that carbon was negative? How does that work? Okay, we have, if we call this the red 2 are explicit. Okay, you said hydrogens. Okay, so let's imply 3 hydrogens, right? 4 minus 2 minus 3, that would get us a negative 1. 1, 2, 3. What's the problem? Exceeded octet. So can it have 3 hydrogens? No.
I know it could. I don't know what else it could do. Our lone pair is implied then.
What if we subtract 2 electrons from a lone pair? It'd still be neutral. Minus 1 hydrogen. Okay. And you're right, that's challenging to piece out. That would be a very good reason why someone would suggest maybe we should memorize our common bonding patterns so that when we see these things, we know exactly what's happening around them. Not to sound like a broken record. Okay. Or we just accept the loss, and that's okay too. You can accept that loss. Okay. In the grand scheme, that isn't a huge loss, I would argue.
What would be the hybridization for the NH2?
So that nitrogen, what's its hybridization? So first and foremost, we should make sure what? Octet. Does it have its octet?
Not shown.
It's not explicitly shown, because if we drop in 1 hydrogen, the second hydrogen, it doesn't have its octet, which means there's an implied lone pair. Now, when I go through to try and deal with the hybridization, how many groups of electrons are around that nitrogen? 4, which means the hybridization is sp3. Oh, you're going to ask the same question? And so, yeah, what you're trying to piece together is what is that larger structure, okay, the non-implied structure, and then what does that mean towards hybridization, which is really just counting the groups of electrons around it. So there's lots of cases where we imply things, and there's lots of cases, yeah, that's actually it. It's lots of cases where we imply things. So you have to be familiar with those bonding patterns. Make sense? Okay, Nate, you started this party. Do you have more questions in this one? Or should we go through and do more mechanistic stuff?
For part 4 with the implied hydrogens, it was the image it's like that. Those are simply hydrogens in the wedges and dashes, right? Because I've seen some cases where it can be CH2, and with it just being the wedge.
So what I believe I just heard you say, if we take a look at our structure on the left, is that that can be a hydrogen.
That's what I'm guessing.
No,
Okay.
that can't be a hydrogen. What is it? It's a carbon. That carbon, because it's the end of a point, unless it's explicitly stated, it's a carbon. That carbon doesn't have its octet, which means that carbon also has 3 hydrogens connected to it. But the end of the point is still a carbon. Okay? If I want that to be a hydrogen, I have to say that's a hydrogen. I would have to say hydrogen. Okay? To what the question is asking you to do, which will get relevant later on, is going through and showing all the implied hydrogens. Okay? So there's 2 hydrogens here. There's 2 hydrogens here. Okay? That bottom one has to have another bond to a hydrogen. That hydrogen must be wedge because I've specified that CH3, which is what's down. That's weird. CH3, which is down below. Okay? If we move to the next spot, right, I have a CH3. I've already specified the dash for the bromine, so the octet at that now red carbon is satisfied, or the red dot. So I can continue to move around. I've got a CH3 up here, which then means I have implied hydrogen down. I have a CH3 here, which means I have an implied hydrogen down. So what we've now gone through and done is labeled all of the hydrogens. Okay? What makes this more challenging is that I want you to then go through and do that on the product. And the idea would be to go through and find the hydrogen that reacted. What makes it potentially complicated? Can I delete all the hydrogens, all the drawings on that? Clean that up. What do you think makes this more challenging?
The first thing I think of is the reactions we were going over and how when you created that pi bond, a hydrogen had to be affected.
Cool. So this is good getting into the current content. If we look at the change, we see the formation of a pi bond. Formation of a pi bond is an elimination reaction. And in the elimination reaction, what has to happen? Number one, we do form the pi bond, but we form the pi bond by breaking 2 sigma bonds. And as you correctly identified, one of those sigma bonds is usually to a hydrogen. Why is it really important to know where your hydrogens are? So that you can tell what's flipping happening in this reaction. Which hydrogen was removed? Okay? Which is what the question is getting at, but it's also adding another layer that makes this more challenging. What's that extra layer? And this now may be just so long ago that we aren't processing it. Okay, where we started was what's the relationship between drawings? Okay, understanding the 3-dimensional space for our molecules. Why would this question be appearing in a 3-dimensional space question? I have a circle with 4 probes attached to it. I have a circle with 4 probes attached to it. What's different when we look at reactant to product? It rotated. Okay? That simple rotation can make us think that a pi bond formed here. Because look, right? If we just look at that ring, it formed there. Is that the same space? Nope. Okay? So what we're trying to do is realize that our molecules, whether we want them to or not, are spin, flip, and rotating, which means the drawings that we draw, we have to acknowledge that we could spin, flip, or rotate. So we absolutely have this pi bond forming, but where is that pi bond forming in the starting material? If we've identified our reaction type, it's an elimination, form the pi bond, break 2 sigma. I lose a hydrogen. None of the hydrogens are specified, so that's easy. What else is lost in an elimination? The bromine is lost. So if I'm going to go through and make my pi bond, it's the connection between two carbons, the carbons where the hydrogen was lost and where a bromine was lost. The bromine is explicitly stated, which means the pi bond is either forming here or here, purple or blue. Okay? Because we've done a rotation of the molecule, it now becomes a little bit harder to determine which of those places it actually happened. Okay? So now it's trying to reason through where it happened and why and all of that fun stuff. And that's why I want you to be able to look for those hydrogens to say which hydrogen was removed. And if we push on that a little bit, hopefully what you can see is the hydrogen that was removed is out here. So that when we form the pi bond, we're forming it between the outer two spokes, not inner two spokes. Right? If we think through the spokes on this ring, there's 4 spokes. The blue space would be forming it on the inside of our spokes. Look where the double bond is. It's not on the inside of the spokes, it's on the outside of the spokes. Does that kind of make sense? Okay. And what's happening is we're taking that 3-dimensional stuff that we learned about with structure in Unit 1, and we're now overlaying reactions on top of it. Okay. Absolutely, the difficulty jumps through the roof because you now have to be able to deal with what those 3-dimensional models were and what they meant and now apply these definitions over the top. Vastly more challenging. But that's why we talked about structure first. And so the idea is that we're still building on that structure. We're still constantly working on it. We're still using structure to interpret these things. But now what we're trying to do is take it to the next step. And the next step, okay? To that, take it to the next step. I would argue there isn't another step after this. They're just different steps. Because what we'll do is take our structure and instead of doing an elimination, we'll do an addition. We'll do a substitution. So it's not a new step, it's just a different direction. So what we've started is building up, and now what we're going to do is still on that foundation, effectively spread out. But we're not going up in difficulty anymore. It's just looking at how it applies in that new environment. Okay? That's still a lot of stuff. Right? That doesn't make it easy. But we aren't saying, well, and then what do we do? And then what do we do? No, it's we've built up to this point. You now have the fundamentals. It's now what are all the things that we can do with this information without scaffolding higher. At least that's how I envision it. Whether or not that holds true, we'll see what you all think. Does it kind of help? Was that your question? That was your question.
Yeah. It's a lot.
It is a lot. Okay. Do you feel a little better about it, Shay? Because you were...
So, I just don't get why it's on the inside and on the outside. That's what's really throwing me off right now.
That question statement is a little bit different, I think. So if I just take a circle, do this, this, and I draw a circle for the product, actually not even that. Do the same thing for the product. Here's a circle, line, line, line. See all the connections? In my product, I want to put a purple here. Where is that in my reactant? Should that be placing it here? Where should it place it then?
Okay.
For it to match, it needs to be here, or, because there's an or, it needed to be up here.
Can't be the box in the middle. Okay.
Ah, there it is. There's a lovely statement. Okay, so recognizing the inside versus the outside. The inside didn't make any sense, right? Because if we look at our thing, where's the purple? It's on the outside of our spokes. It's not on that very inside. Everybody kind of agree with that? Okay. But then the question is, should my purple be here or should it be, we'll call it green now, here? Both the purple and the green are now outside on my reactant. Everybody see that? Which one caused the purple? Should it be the green part or the purple part? People saying the green, well, didn't I just take this and just turn a little bit? Shouldn't I be coloring that green? Okay, which is a fair observation. I completely agree with. But why should it be the purple? For an elimination reaction, I form a pi bond by breaking 2 sigma bonds. One of those sigma bonds needs to be to the bromine. Is the bromine connected to the green spaces? Nope. Which means the purple had to be this one, not there. Kind of, sort of? Which makes this extra fun, because when we look at this, I know, fun, weird, okay? It isn't just a rotation of the molecule. What happened is we did the product, and then we took the molecule and we went, whoop, and we flipped it over, and then drew that and said, what happened? Right? Well, why did we do that? Are you responsible for the 3-dimensional rotation, spin, flips? Yeah, that's why. Okay? So it's layering in, again, that Unit 1 content of how do we build that out. Okay? So you should fully expect to see things like this. You should also expect that I do some questions that aren't as magnificently jerky and say put the bromine up there, so it's really straightforward. The core structure maintains the same orientation. It's just where that bond is happening. Because we're now testing at 2 different aspects. Kind of, sort of? Okay. Next question.
When you ask questions on the exam, will it differentiate between intermolecular forces and intramolecular forces? Because I know we look at the forces, the bonds in a molecule, but then we can speculate the possibility of forces between other molecules.
Yes.
And I just feel like I get a little confused if there was a question about it, and I could answer it wrong based on the bonds or the forces.
So for the sake of the recording, it's how is a question asked where you could potentially confuse bonds versus forces, ultimately going back to intra versus intermolecular. When do we care about forces?
And there's multiple molecules.
But when I run a chemical reaction, don't I care about multiple molecules? When do I care about forces? Say it again. I do care for melting point. How is melting point different than a chemical reaction? The problem is they're very closely related. It's just why are we asking at different points? This here, with how that is drawn, you're using both forces and bonds. You're constantly using that. Because if we go through and look at how this reaction works, the hydroxide is attracted to that hydrogen. That's a force. If it is attracted enough that the electrons break and go with the carbon, now it's not a force anymore. In big air quotes, it's now talking about bonds. okay? Because we're making and breaking bonds. If the only thing I care about is forces, I don't make or break bonds. The identity of the molecule must stay the same. Well, when does that happen? It happens for melting point. When else does it happen? Solubility. When else does it happen?
I forgot the other things.
Boiling point. It's really just melting point, boiling point, and solubility. Those are really the only two big categories. So you see a question asking about solubility, all I care about is the forces. Okay? You see a question about melting point, that's forces. You see a question with a reaction arrow or curved arrows, that's bonds. Okay? To answer the question about solubility, that's forces. But how do you know what forces you have? You're still going back to the bonds. So they're all very interconnected, but I think ultimately what you're getting at is, or asking is trying to differentiate when do I only need to be worried about forces as the primary category versus bond breakage as the primary category. Bond breakage is a chemical reaction. That's curved arrows, that's mechanisms, that's reactions. Forces is melting points, boiling points, solubility.
Okay.
I think that addresses your question.
Yeah.
Other questions?
When we're studying, what exactly should we be studying? The play posits, the slides, the documents that you put together, and the active?
Yes.
Okay.
And this becomes an interesting question when it comes to studying.
Yeah.
When you study anatomy and physiology, what do you do?
A lot of flashcards.
Flashcards. Okay? Because what are you doing?
Memorize.
You memorize a fact. Absolutely. Is that what you should be doing for OCHEM?
Definitely not all the time.
Yes and no?
The vast majority of the time, it isn't a flashcard. It's practice. It's how do I apply what I've memorized to a new scenario? Because every question you get is a new scenario. It's a new scenario. It's a new scenario. And so it's coming up with a system when you see the practice, how do I navigate what's happening within that? Glad I opened this instead of the last one. So that when you see that worksheet, I think I have the worksheet open still. What was I going to ask? So that when you see that worksheet, that what you are focused on is this becoming this. As a secondary, these pieces weren't involved in the chemical reaction, or at least not apparently involved in the chemical reaction. How do I ensure that they absolutely weren't? Well, I would ensure they were absolutely weren't, because when I run this chemical reaction becoming purple becoming red, that I've mutated the structure a little bit. Does that mutation necessarily mean those blue things are identical, or did they also change through the course of the reaction? So what we're doing is starting where the chemistry is, ignoring everything else, trying to address just what's in that tiny little area. Once that is addressed, then reconcile the rest of the molecule to ensure that something else unforeseen didn't happen. Okay? So what you're trying to build up as practice is selective vision, so that when you see this question, you aren't seeing it as this, you see it, and I would almost argue that you start there. Why is the rest of it irrelevant? Why should that, and I would almost even argue, why should that be your focal point?
It's not on the other side of the reaction. I mean, it's still not on the other side of the reaction.
Well, but nothing's on the other side of the reaction, so I could say predict the product.
Because the stuff you erased is the same.
Why should my focal point be there and no other part of that drawing? not carbon or hydrogen starts to get at it, why would I ignore carbon and hydrogen? It's freaking OChem. Shouldn't I be paying attention to carbon and hydrogen? No, I don't. Why not? What is different about carbon to hydrogen versus carbon to bromine? There's a why is there a reactivity difference? Differences in electronegativity. That difference in electronegativity, we would manifest the carbon to bromine bond being a polar covalent bond. Why should I look at the carbon to bromine bond? There's a large difference in electronegativity that ideally I'm seeing as polar covalent first, then recognizing there's a large difference in electronegativity. This gives me two sources of reactivity, that bromine being negative and that carbon being positive. Now what I could start to do would be to layer in more information. If I was given the product, I could look at that product and be, what things stand out in that product? What should be my selective view in that product? The pi bond. So all of this disappears. Okay? And now my focus is just on that pi bond. If I'm running a chemical reaction, because this is a reaction arrow, I should now also change my viewpoint now on the starting material, because the pi bond is the connection between two atoms. Well, I have two atoms. Is one of those atoms bromine? No, which means I have to expand my view to include at least one more carbon. Now I can say, okay, well, how could I make that pi bond? What has to happen? Making of a pi bond was an elimination, which means the loss of the bromine, which I see here. It also means, because I've memorized that definition, the loss of the hydrogen. So I now have to look for a hydrogen nearby so that I could remove that hydrogen and make that pi bond. Well, which hydrogen should I remove? Should I remove that hydrogen? Should I remove that hydrogen? Should I remove that hydrogen? That's three choices. How do I know? Well, we can pull some of this information back out. We now expand the view. Is the double bond happening out to a CH3? No, which means that hydrogen's not relevant. Okay? It's somehow happening internally to our ring system. Okay? Now the question is, where internally to the ring system? Now I have to pull more information out to get a little bit more structural information. Okay? Is the double bond happening in between three methyls, or is it just happening at the end? Okay, well, I had to pull out a little bit more. Okay, that looks like it's happening in between. Or actually, no, it's at the end because I unhid that one. Okay, so it's at the end, which means this needs to be the hydrogen that's removed. If I'm now being asked for a mechanism, what's the point of the mechanism? Show how the electrons flow to make that pi bond. So we can go back to our starting, because we've identified all these pieces, and now start to say, how did that happen? Well, what bond do I know had to break? The bromine. Didn't I know the hydrogen had to break too? Why do I look at the bromine, not the hydrogen? The difference in electronegativity. Bromine was more electronegative than the carbon, which means that bond is already breaking. Bromine is already taking those electrons. If it takes those electrons, what happens to our carbon? Positive. Do I have electrons to make a pi bond if it's positive? No, so what do I have to find? Electrons from somewhere else. What other bond has to break? A bond to a hydrogen. That bond has 2 electrons in it. Where do I want those 2 electrons to go? To making a pi bond. So let's say those electrons go to make the pi bond. What happens with those arrows? What we're saying is now H plus is chilling out over here, not connected to the structure. Cool, I've started to draw a mechanism based off of differences in electronegativity and just identifying those bond polarities. Now comparing back and forth, trying to predict those differences. Okay? There are plenty of cases where if I just look at a carbon-bromine bond, it could do a couple different things. In fact, it can. Okay? It can do two different things. It can do substitution or elimination. How do I know which it does? I would need context clues somewhere else. In this case, I had the product, so I selectively look at the product. And we built out what we saw. Does that make sense? Okay. The problem with what I just did here is we erased the structure as we went through and moved through it. And you can't do that on an exam. You see everything. What you have to try to do is reduce your stress to only focus where the chemistry is appearing. How do I know where the chemistry is appearing?
You look at it,
What am I looking for to know chemistry is appearing?
changes,
What changes?
and more electrons.
The differences in electronegativity. Those differences in electronegativity are what dictate it. Okay? That gets me the reaction. The drawing, I can then start to draw those atoms. How do I know where the bonds are supposed to be placed? Well, that's going to go back to how we draw Lewis structures. How do we build those out? How do we represent those? That's why we had to address all of that early on, so that we now have the way to represent these changes moving through. Which is really cool, even if you don't think so. But it is really cool. Makes you feel better. I don't like testing on it just as much as you don't like getting tested. Doesn't do much. It just puts us both in misery, but for different reasons. Okay? With that, we are done, so I will go ahead and stop. Okay?